So, good morning. I'm here to talk about JSON parsing. So I work at ThinkCell. We are a company. We sell a plugin for Microsoft PowerPoint that makes it easier to do data visualization and stuff like that. And just like any big application, at some point we need to parse JSON. We're dealing both with JSON that comes from the user and also over the network. So we call some APIs to get some data and parse the JSON. And we want to turn, as usual, that JSON into our own data structure so we can work with that further. And while there are like dozens of libraries out there to parse JSON, that hasn't stopped programmers before, right? Telling a programmer there's already a library to do X is like telling a songwriter there's already a song about love. So naturally, we wrote our own JSON library. It's on GitHub. So we've got like this boost-like extension to the C++ standard library on GitHub that we use in our product. And as part of that, I've recently open sourced our JSON parser. So it's a fully validating pull parser. But fully validating means that usually you don't care about all the JSON data, but only want some individual fields. But it's fully validating in that it will also validate fields as you skip over them. What exactly a pull parser is exactly the topic of this talk. It's quite fast, so there are some benchmarks. On the left, take them with a grain of salt, because I've written the benchmarks, and of course I picked one where the library looks good, right? So here we are parsing, we've got a big JSON document, some animation data or something, I believe, and we wanted to extract individual fields out of there, and the time lower is better. So ThinkCell is on the very left, then we've got enrollment.json, rapidjson, boost.JSON, and finally simdjson. So simdjson is faster, but simdjson is also cheating because simdjson doesn't do full validation. If you skip over a huge array, it will not look at the characters at all and just skip over the end of the array. So naturally, it does less work, so it's faster. It also does more simd tricks than we do. So. Our parser has O1 memory usage, so it doesn't do any dynamic allocation and only needs to remember essentially the current input position besides the data, of course. And it allows you to sort of implicitly define a schema. More on that throughout this talk. So this is a talk on the software design track, and I didn't want to make it just a 1-hour advertisement of our JSON parser. So we will look at a bit at parser design. In particular, we're going to answer the question, what is a parser, or rather, how should you write a parser? So it parses JSON. In case you went to this room by mistake, JSON is JavaScript object notation. And the idea is it's a human-readable serialization of JavaScript objects. So let's look at the various JavaScript values there are. So in JavaScript, there are primitive values like null and undefined, Boolean values, strings, and numbers. And then we also have objects. Objects are a collection of properties, so essentially key value pairs. And you can define your own objects by giving names associated with values. You can have arrays, which are special objects where the names are indices, so you can omit them. Functions, which are just objects that you can call, and so on. So all of JavaScript is composed of those things. And JSON is essentially a subset of a JavaScript literal. It's not really a subset. There's some caveat about white space, but we don't need to worry about that since we're not writing JavaScript. So this is an example of JSON. It describes me as a conference attendee, and it is also the example that we're going to use throughout this talk to extract data out of there. Formally, JSON has a quite simple grammar. It fits on the slide it almost fits on the slide. So in a nutshell, a JSON value it can be null, true, or false, corresponding to null or Boolean. It can be a number, it can be a string, it can be an array, or it can be an object. If it's a string, it's simply a bunch of characters behind quotes, and this also supports some escape sequences, the usual ones like \n and so on. A number, I can have an optional minus sign, then we've got a mandatory integer part, so some digits, an optional fractional part, and an optional exponent. And in particular, JSON doesn't distinguish between integer numbers or floating point numbers, they're all just numbers. There also isn't any range of values associated with JSON, so the number can be arbitrarily large, and it's up to the parser to figure out what to do with it. An array is simply a comma-separated list of values in square brackets, and an object is similar, with just curly braces, and we additionally also have the name of the value. And that's essentially the entire grammar. Like I've omitted white space in there, and the definition of digits and characters or escape and so on, but that is JSON, right? And it's such a simple format, we can write a parser in a very straightforward way. So this is the really basic parser that simply takes a string and skips over it until it reaches the end of the JSON. So it doesn't do anything with the data. So we can write it by one function for each production of the grammar. So to parse a value, we take the string, check if it's null, true, or false. If so, we're done. Otherwise, we check whether we have something that looks like a number, then we start passing a number. If we have a quote, we start passing a string, array, or object accordingly. And for example, here just object, so we skip the curly brace. While we haven't reached the end curly brace, we skip the name of the key, we skip a colon, we skip the value, and then we skip a comma. And this doesn't do any validation on like trailing commas, but like the point is, it's not that hard to parse JSON. The actual part of where you iterate over the string and skip over it, that's not hard, right? We can now do that. So the complexity in parsing comes when we look at it, how it's parsed in JavaScript. So we've got our JSON at the top, and we want to parse that in JavaScript. We just call JSON parse, and it will give us an object. And then we can, to get the name, we just write object.name. To get the subtitle of the first talk, we index into talk and get the subtitle. And we can, if we access a key that isn't defined, we will get undefined as a result. So the JSON parse function in JavaScript takes the JSON as a string and dynamically creates an object. And that is very convenient and also impossible to do in C++, right? We cannot create an object at runtime. We cannot create a struct from string data at runtime. So all the complexity in the actual parsing in C++ is in the return type of the parsed JSON function. So we take the string. We know how to skip over the JSON in there. That's not the hard part. All the complexity is what do we return in the result. This is where all the design decisions are. This is where the libraries actually differ. Sure, like the implementation, some of them use more SIMD than others and so on, but like in a nutshell, the parsing itself is not the problem. It's the interface. So let's look at the interface. The most straightforward one is a JSON DOM parser. What DOM stands for is not important because it also has nothing to do with JSON. It's just that's how this kind of parser is called. So the idea is, well, we try to represent the JSON value in C++. So we call parsed.JSON, and it will give us the JSON value on error. So what we need to do for that is we need to sort of map the JavaScript values to C++ objects. It's very straightforward for the primitive form, right? Null is null pointer. Boolean is bool, and string is, let's say, std string. Number is more interesting because, as I mentioned, JSON doesn't define any range of numbers. So it could be a floating point number. It could be a big integer or whatever. Like there are various options. And usually libraries say, okay, if it fits in an integer, we make it an integer. Otherwise, we try to create a double or something. But we need to make a decision here. At that point, we could imagine like a template parameter to specify the number type, whatever. But there's a trade-off here. JSON arrays are dynamically sized, so we use the std vector of JSON value again. So it's a tree-like data structure where we use the value recursively. And then object is a collection of key value pairs, so we use some sort of hash map. We could use the standard one, but the standard one is quite slow. The boost one is much better. But in a nutshell, like it's a mapping of names to values. And then a JSON value itself is just a variant of all of those types, right? That is what JSON is. And now we can write a parser that parses JSON and returns us a JSON value that corresponds to the document. For example, boost.JSON looks like that. So we've got a parse function that returns a boost.JSON value, given a string. And it's a bit smarter than that, so it doesn't use a variant, it doesn't use a hash map, it doesn't use a vector, like it uses custom types, it supports allocators and so on, so it's more optimized in the data structure than the naive one, but in a nutshell, this is what it is. And the library is designed that this boost.JSON value type is sort of meant to be a vocabulary type, right? This is the JSON type that you pass around at the interface. So you've got functions that consume JSON, they take boost.JSON value and work on that. So example usage can look like so. So we create our JSON again, parse that, and then we know that the top level thing is an object, so we call sObject to get us sort of the object part of the value. And then we can index into the thing using add, doing some typecasts when necessary, and print them all out. And it very much looks like the JavaScript code. It's a bit more verbose, and instead of undefined, we get an exception. But there are also different interfaces to check keys that don't exist. And this is a very straightforward way to parse JSON, to use JSON to convert it to the appropriate data. However, one downside is that the JSON value itself is a stringly typed thing, right? Because the JSON value comes from runtime, we cannot put it into the type system directly, so we have to emulate it at runtime. This requires dynamic memory allocation, right? We have to use a hash map of names to values. We need to store the names of the fields and can't have them elide at compile time. We need to do manual error handling of the JSON content, right? When we want to access the talk field, it might not be present because the JSON is missing some entries. So we need to handle that on access. So we still need to do some error checking, either like have exceptions or manually check it and use default values or something. And all of that is completely unnecessary in most situations. This is because you don't want to work on JSON value directly, right? You've got types like that. Like you want to pass our JSON into the structs that we read. So we can use the structs in the rest of our code base. And so what we really need is sort of two functions with this approach. One that parses JSON into JSON value. And this is the one that's provided by the library. And then another function that takes the JSON value and returns the actual struct that we want. And this is essentially like a handwritten parser, like we're still doing parsing. It's just that the input is more structured. But we need to check, do we have the field that we expect? We need to handle errors. We need to iterate over that appropriately. Like we're writing parsing code. So the DOM JSON library, like it hasn't saved us a lot of work. Right? We still need to do parsing, just parsing in a slightly different way. So this is only really useful, and by useful I mean like absolutely required in sort of two situations. The first is when you want to implement generic algorithms over arbitrary JSON data. For example, JQ. Who here knows about JQ? Okay, so JQ is an amazing tool. It's essentially like a SQL for JSON. You give it JSON data, you give it a query, and it returns you the value of that thing. Like my entire window manager is powered by JQ. And it's a great tool, but it takes both the JSON as input and the query as input. So it cannot have any compile time known scheme. It has to operate purely on dynamic values. And there, like boost.JSON can be really useful. And I believe this is also what the library was designed for. Like it's meant to be used in like web contexts where you need to deal with JSON requests and handle them and send them as payload around. So we work on arbitrary JSON data without a known schema. And then this is sort of like an edge case that I've just put in their completeness. So maybe you need to do multiple parses of the JSON data and the parser is too slow. So you parse it once in like a pre-cached way and then you access the cache. But this is like a rare situation. But if you're not in either of those situations, like a JSON DOM isn't really what you want, right? You want a C++ type, not a JSON DOM. And when we go this way by creating the DOM, we've got all these dynamic memory allocations, which are just temporary because we then immediately throw them away after we've extracted the appropriate data in the format that we wanted. So can we avoid them? This is where second approach for JSON parsing comes in. So JSON Zax parser. What Zax stands for is also not important, has something to do with XML, not with JSON, but this is just the way the parsers are called. So the idea is that we sort of do event-driven parsing. So our parse JSON function takes the input range and then a JSON handler. And as it parses stuff, it invokes the handler and passes it the data it encountered. So this can look something like that. So we start parsing the JSON document, see the opening curly brace, and emit the sort of object beginning event. Like because we just seen the beginning of an object. Then we see a key, so we emit the appropriate key. Then we see a value, which is a number, so we say we've just seen the number. Then we've got another key value. This time the value is a string. And here the value is a Boolean. Then we've got an array. And while we could say, OK, we've seen an array, here's the std vector of the array, this would do a dynamic memory allocation and a copy, which is what we wanted to avoid. So we sort of say, OK, so we've seen the beginning of an array. And then the next events form the individual values of that array. So here, the next thing is a sub-object. So we emit another object begin, key value pairs, object end. And by the point of this object end, we've reached the end of the value. And the next sort of event would be the next value in the array. So we've got this sort of implicit bracketing structure with the object begin and object end to identify where one value begins and one value ends. Here we're just done. So we emit array end and object end. And this is really like a flat list of events. I've just indented them here to make them. Yes? How do you handle the nested what?
Nested arrays.
So nested arrays, yeah. So we have a nested array. For example, we could imagine that the second element of the array would be another array. And then after the object end there, we would emit another array begin. And then we would emit the events for the thing. And then we emit the array end when we reach there. So we sort of like nest array begins and array ends within the array begin and array end. Does that answer your question? Okay. Yes? Do we have any kind of events between links? So by our parser doesn't work like that. Like I'm just showcasing the idea. And yes, you would want some sort of events between parents for the reason that will become obvious when we start the way to look at that. But this is just, I'm just showcasing the general idea behind this parser. I've seen, OK, maybe it was just the light. OK. So we've got this list of events. And then the handler can just be, let's say, a bunch of virtual functions. And they are invoked when we reach the appropriate event, and you can override them and do the appropriate logic. And this is, for example, how rapidjson Zex API works. Like, so we've got the parser is called a reader, and there's a parse function which takes like the input and then handler, and essentially it will invoke the appropriate function of the handler, just as you've seen. Just like they're just using a different naming convention than the handler I've shown you, but otherwise it's completely identical. And this is also the one that we previously used at ThinkCell before we migrated to our own one. So how do we use that? Let's have the same example. So we've got the conference attendee data, and we want to print the name and the subtitle of the talk. And it looks like that. So we create our custom handler and override the onString method, because all our values are strings, so we want to print them. And because we don't have a link between the parent, we sort of need to keep track of the current object stack where we are. So if we have a key that is the last key was name, and we're inside the top level object, then the value of the string is the name, and so we print it. If the object stack is like top level, if we're inside talks, and the last key was subtitle, then we can print the subtitle. And then we need to override object begin, object end, and key to sort of keep track of the object data. And this works. It doesn't quite do what the previous DOM did, because it will print all subtitles and not the first one. So you would need to extend it to keep track of which array index you're in. And while this works, right, this is not nice code, right? It's incredibly annoying to use. Because you've lost all of this context, right? You're just dealing with flat list of events. So we're getting a string. What is the string part of, right? What's the corresponding field? So we need to keep track of the state machine manually, which isn't nice. It's also really awkward to return results, because if the handler wants to return some data, that is returned to the parser, right? And then we're in the middle of the parsing JSON, and we also got some random data from our handler, and the parser can't really handle that. So we need to store the data in our handler and then return that at the end, right? It's just not really nice to use. But the upside is, right, they're faster. Like, we don't do any dynamic memory allocation. Like in the benchmarks, the rapidjson parser, that was faster than the DOM. So let's put a pin in that and talk about something completely different. Range algorithms, right? So let's say we have got an input of vector int, and we want to remove the odd integers, square the remaining ones, and print the first square that is divisible by 3. Okay, this is how we can write that function, right? We take our vector, we iterate over it, we skip the ones that are odd, we square them, and if we found a square that is divisible by 3, we return it. Otherwise, we return none, right? Straightforward, good. So this code is nice. It generates quite intuitive assembly, like you can look at that and just understand what it maps to. However, it's also nice because it does lazy computation, right? Once we found the first square, we don't compute more squares. Once we have an odd integer, we don't compute its square, and so on. So it only does lazy work as much as we need it. But of course, the downside is it's not really composable, right? We want to write a function that does essentially the same but slightly different. We need to repeat a bunch of code. So we can fix that by using C++98 algorithms, right? So we identify like atomic reusable algorithmic building blocks, extract them in functions, and just call them. And with the C++98 algorithms, it can look something like that. So we've got a compute function that takes a std vector of int. Because the algorithms modify data in place, we need to create a copy. Then we get rid of all the odd integers. Then we square the remaining ones. And then we find the first one that is divisible by 3. And that one also works. So this code is nice because we are composed of smaller building blocks. Like we've got the evasive, we've got the transform, we've got the find. But we need to do intermediate allocations. Right? We cannot modify the vector directly. We needed to create a copy to modify it. And we're also too eager. Like we compute the squares of all integers, even though we only need the square of the first one. In fact, we wouldn't need any square because like divisible by 3 is maintained by squares, but whatever. Right? We're doing more work. Now, the way to fix that, I think you know how to fix that, but bear with me for a bit because this is a talk. Let's look at a different way to fix it first. And here the idea is we don't store the intermediate results. We just immediately pass them to the caller. And I think you might know where I'm going on with this tangent by this point. And the way this one looks is we sort of implement internal iteration. So we've got two kinds of ranges. We've got the one where we can just use the range-based for loop. And then we've got the other one where the range is a function that you can call. And when you call it with the for each sync, it will invoke that sync with each value. And then to do early return, we just use like a break exception that you can throw to terminate the loop. And with that, we can write filter. So a filter takes a range and a predicate, and it will invoke the sync with only the values where the predicate are true. So it returns a lambda that is given a sync, and then we call for each on the range object, and only forward the values to the sync where the predicate returns to. And this filters values out of the range. And it's like a quite complex implementation. We just delegate the actual traversal to the underlying range using for each. So likewise, we can do transform. So transform takes a range and a function, and it will invoke the sync with the transform value. So this also returns a lambda that takes a sync, and then we call for each, and then we pass that on to the sync. And we can compose them to solve our problem. So we create the even squares using nesting of transform and filter. Filter is sort of the opposite of remove if, so we have to negate the condition. And note that the second line there, it doesn't do any work, right? It just creates a nested lambda. We only start doing work when we call for each on the range, give it our sync, because we can't do find if, because find if requires iterators, but we don't have any iterators. And we also can't use the range-based for loop because it doesn't work with callable things, right? We have to use our for each. We call it with the sync. We check whether we found the first square, store the result. We have to lose like an output value because we cannot directly return a value from there. And then we break. And this will stop everything, and we return the result. So this is still a composition of smaller building blocks. It's still lazy, right? We only compute as much work as necessary. But we can't use the native for, we can't use range algorithms, so it's a bit of awkward to use. Short circuit is also more complicated, so here we're using exceptions. We could also imagine error channels. So there are some advantages to using internal iteration. I think so we use them extensively, using error channels instead of exceptions. But they're still a bit awkward to use, but in the situations where we use them, like it's worth it. Like it's a lot easier to write using iterators and sometimes faster in certain situations. But of course, this isn't the solution that you expected. So what you expected that we were to use C++20 iterator ranges. So here again is the idea is we lazily compute values when required by the caller. So instead of pushing everything to the caller, we just have the iterators, and when we increment them, we do the actual work. So we also need filter for those. So filter is a custom range with a custom iterator type. It does nothing on dereference, so it just forwards because filter doesn't change the value. But when we increment it, we increment parsed until we found a value that doesn't match the predicate. And similarly, here's transform. And again, it has a custom iterator. The dereference does a transformation on the thing, and then the increment does nothing, just forwards because we keep incrementing. And with that, we can solve the problem as well. So we filter and transform are big. Then we can use findif because we still have iterators, right? It just works. So findif works, and then we return it. So a small nitpick. I never really liked the last line. So findif returns an iterator, but in most cases you don't want an iterator, right? You want some. In this case, we want an upstell of the element. So at Thinkcell, we have like custom algorithms which take like a range return. And here we say we want to find the first one, and we want to return the value or none. And this will directly give us an optional. Similarly, we've got something like give us the slice of everything before the thing. Like there are like dozens of these range return values that return slightly different combination of types, which makes it really convenient in situations like that. But with this approach, using iterator ranges, we still have the composition of the smaller building blocks. We're still lazy. We can use the native for loop. We can use the range algorithms. They're quite convenient to use. So what does this have to do with JSON parsing? Well, there is sort of a correspondence, right? The handwritten implementation, this is like we were to write a handwritten JSON parser just to parse the individual data that we wanted. So every time we want to parse JSON, we write a function that takes a string and just parses the JSON. The C++98 algorithms with the immediate allocations and the eager copies and so on, that is a JSON DOM parser, right? We create an intermediate data structure to do the work. We still have generic code, we can outsource this, but we've got the intermediate allocations. The one that you found probably slightly weird using internal iteration, that's a sex parser. Right? When we get values, we invoke the sum handler to get the value. And what we really want for JSON is like the equivalent of the iterator range, right? Because that was the convenient one to use. So we want a parser that sort of behaves like an iterator range. So to get there, let's dive into what is exactly the difference between internal iteration and the iterator ranges. So internal iteration is a push model. We've got some algorithm, the algorithm computes data, and as it computes the data, it will invoke a handler. For internal iteration, it's just a sync that is invoked of the value. And for a sex parser in JSON, like we've got the various different events that we can trigger. But the thing is, the algorithm is in full control. Like the algorithm just keeps on computing and invokes the handler, and there needs to be like some back communication channel if you want to stop that. You cannot, while it's computing, like you can't stop the computation halfway through, do something else and continue. Right? The algorithm is in full control. And this makes them slightly awkward to use. Right? So we want iterators which behave the opposite way. They have a pull model. Here, the algorithm only computes the next data when the user asks for it. So the user asks for it in the iterator model by dereferencing or incrementing the iterator. And as it does that, this computes actual work. Right? And this advances the state, this advances the computation. But crucially, the user is in full control. Right? The user can get some values, do something entirely different, come back later, get some more values, do something else. It wants to outsource something into a function, it wants to return values, it wants to stop altogether. Right? Its user is in full control and not the algorithm. And again, like this, the missing JSON thing here. The pull model is more simpler in Rust. So a Rust iterator just has a single function item, and this will give you the next thing. So when you call item, it will extract the next, compute the next value, and returns it, otherwise, or null out when it's at the end of the thing. So the user just keeps on calling item to get all the data elements. And we want to write that for JSON. And this is a JSON pull parser, and this is exactly what we've implemented. Yes?
Maybe you will answer this later, but does this depend on order in your object?
Does it depend on the order in objects? I will get to that. So the idea, the parser is fully driven by the user. We keep the user in control, which means we no longer have a single JSON function. We've got a JSON parser object, which has a bunch of functions that you can pull the data. Pulling primitive ones is easy. So we can have a function null. You can ask it, and it will return you whether it just consumed a null. And for the Boolean, it will give you the value. So it returns an optional bool. Like really, the return type of null is sort of like an optional null pointer, right? Or an optional void. And the implementation, so the parser just needs to maintain two pieces of data, like the current position and the end. And for null, we say, OK, if we just skip the string null, then we found null and return true. Otherwise, we return false. And for the Boolean, we return, we skip true or false and return the appropriate value or null out. And as you can see, like the difference between like the range pull parser is that with the range pull parser, we've got a single thing, item. Like, give me the next item. But with JSON, we've got different kinds of values. So we've got different kinds of methods, one for each item. String works similarly. So when we have an open quote position at the current position, we will consume everything until we found the corresponding closing one. So we've pulled it, and then we return the string. Right? It's a bit like at what point do we return the string? Like a similar question was with the sex parser. How do we return the string? So we could use like a string view or subrange, but that doesn't work with escape sequences. So in JSON, like \n is a backslash into an n, but we want to turn that into a single character, the new line character. So we could use this .string, but this does an eager allocation into copy. So instead, we can use like ranges code. So in our implementation, we returns a decode adapter, and as you iterate over it, it will decode the characters. Crucially, by the point we iterate over the decoder adapter, we've already changed the state of the parser. Right? We've already consumed the string. And also, we've already validated all the escape sequences. So the decoder adapter can assume that everything is well-formed, doesn't need to worry about errors, and will just give the appropriate characters. So when we've got the JSON that is just hello \n world as a string, and we say, OK, we want to pull a string. And if we got that, then we can iterate over it and print the individual character, and this will translate the \n into a new line and works as expected. With number, we've got a similar thing. So here, again, we've got the problem with what's the range of the number. So we've got two overloads of number. The first one returns the number as a string. So you can then iterate over the individual characters and parse them as you wish. Or you have a number t, and then this will convert that into the appropriate type t. So you can say, OK, I want to pull the number as a string, and then iterate over each character. Or I want to pull an int, and I want to pull a float. And the last one, they also do overflow checking. So if we have a number, but it doesn't fit in an int, then this will not trigger. And again, the complexity here is what happens with objects, what happens with arrays. So for an array, we've got two functions, array and element. So array, it only deals with like the opening bracket of the array. And returns true if we have an array. And then it consumes the opening bracket and continues on. And element must be called to check whether we have an element. So it will check for the end of the array and also skip the comma as appropriate. So the way you pull an array out of the parser is you call check p.array. So if we have an array, then we loop while we're having elements, and then we can pull each individual value in there. So here we want to pull an array of strings. Right? And this will loop over them and pull all the strings of the array until p.element consumes the closing bracket of the thing, and then we're done with the array and continue on with the rest of the document. Object looks similar. So we've got object, which handles the opening bracket. And then instead of element, we have key. And this one also consumes the key and returns us, besides handling the comma at the end of the object. So to pull an object, we check, do we have one? Then we iterate over all the keys. And then we need to pull the appropriate value. And by that point, we have a key and a value combination that we can process. And with that, we can sort of write the very basic parser that just skips over the input again. So it's actually member function skip value, which is useful when we don't care about a particular value. So we just check all the primitive ones. If you have null, if you have boolean, and so on, we're done. Otherwise, for example, for an object, we need to loop while we're having keys and then recursively skip the value of that key. And then this will then skip over the entire JSON content until we reach it at the end of the document. And the actual implementation doesn't use recursion, so we don't create a Stack Overflow with deeply nested thing, but this is essentially the nutshell. We can also use the pull parser to write a DOM parser. So a function pass value that takes the pull parser and returns the JSON value. And this one, we just check the various cases that we wanted. So if you have null, then we return null pointer. If you have boolean, then we return the boolean. And if you have an object, we sort of create the JSON object by pulling each key and creating the mapping between values and keys. We can also use implement it to implement a sex parser. So we've got the parser, we've got the handler, and then we just invoke the appropriate handler once we pull the data. And this will recursively traverse the entire JSON object and create the appropriate events. Any questions about this approach? Okay. So what is nice is that we sort of found the lowest level of abstraction. Using a pull parser, it is possible to implement both the DOM and the sex parser. It's not possible the other way around. Well, it's possible with the DOM parser, but less efficient. So this is always nice. But the real benefit is when we know what to expect, right? The title of this talk is Expect Your Expectations. And usually you have some sort of schema. You want to pass that into a struct. So you know, at this point, I want a string. And for that, we can use a specialized API. So we've essentially got all the same methods, just with expect. And then they no longer return optional, but directly the value. And if the value isn't there, that's an error, right? So then we can say, OK, at this point, I expect a Boolean. So I call expect Boolean, and this will give me that Boolean. And when there's an error, we have this error handler parameter that looks similar to a sex parser, just for the errors only, and it will invoke the appropriate function. So the first one is for generic syntax error in the JSON, and then we say like null expected when we've got a null. And then you can throw an exception or assert or whatever. And what's really nice is when you set a breakpoint in this handler, like you can directly see where exactly in the JSON document that is by looking at the call stack, by seeing the context, as we will see. So with that, we can write the same example again. So we want to pass the data for conference attendee, so we call expect object because we have an object. Then we want to loop over the keys. So while we're having keys, we're comparing the key because we don't know the order. So if you have name, we expect a string and print it. If you've got talks, we expect an array with one element, which is an object, which has the key subtitle that we want to print. And we ignore other keys, and then we're done. So we assume that we're only having one single array element here, but we can handle it with another loop to print all the ones. And if we're having a different key in the top level that we don't know, then we also just skip the value and continue on. So when we have like call expect string and we don't get a string, like that is an error that triggers an exception. And exactly the same thing like happens with the DOM parser. When we want to call it as a string, but it's not a string, like that is still an error. So like we fundamentally haven't changed anything here. So compared with a sex parser, like it's very easy to return results, right? Just return something from a function if you want to return something from a function, like you're writing the function. You're not invoked by something else. You don't need to keep a state machine because you have the full context. Like, in which object am I? Well, just look at the parent ifs and there to figure out in which object they are. So this is much more straightforward code, but like compared to the DOM one, it's still a bit annoying, right? The DOM one was so nice, so compact. So can we make it nicer? And we can, because we've got the equivalent of iterators, right? And what we just wrote was code that just like sorts an array manually using the iterators. Like, but there's an algorithm for that. Like, we can now write algorithms that operate on the pull parser, right? We can extract individual parts that we need to do often in functions and just work them. So let's look at a couple of algorithms we can write to make this code more convenient. So often we've got like homogeneous arrays. So here we've got an array of ints, right? 1, 2, 3. And we want to turn that, let's say, into a vector of ints. And for that, we can use an expect array overload that takes a lambda. And this expect array overload will invoke the lambda for each value. and the lambda then pulls the value and returns it. And the resulting int thing is a range. And when we iterate over the range, we will pull all the ints out of the array until we're done. And so we can very easily convert that to a std vector. So it's possible in C++23 using std ranges too. And the things in the library, we sort of have this explicit cast to sort of, because we can't add a constructor as a std vector. So we sort of use explicit cast to convert the arbitrary range into a thing. And so we just converted like a JSON array into a vector without any intermediate allocations, without any copies, right? We directly create the thing. If a DOM parser, like, sure, we can have an array, but then we have an array of JSON values and not an array of ints. And then we would need to iterate over the array of JSON values and convert each JSON value separately into an int. Here, we're directly creating the int as we need it. The implementation of expect array is quite convenient to write using coroutines. So it takes the function, then we call expect array because we expect that we're at the beginning of the array. While we're having an element, we invoke the function. The function will then pull a value, return that value, so we yield it. Coroutines, unfortunately, they have a bit of an overhead. So the actual implementation in the things library uses internal iteration, right? So it returns a sync object that can be invoked for each element, then we invoke the sync. So that makes it very convenient to parse arrays. How can we make objects more convenient? Or are there any questions about arrays? Okay. So, yes?
So, on slide 72, you are basically, here you're basically specifying the std vector of int for the output of vector 2, right?
Oh. Yes, so we specify vector int the output of the thing. So ints is a range when we iterate over it, it will give us ints, but we want to convert that into a vector of ints.
But I understand, like technically,
yeah.
you need to do this, but wouldn't it be ideal if you could get away with just basically inferring that from the expectation?
Yeah, so the question is about whether it's possible to infer that we want a vector of ints. So there are two layers to that question. So the first one is like in the std ranges 2. Do we need to write like int in there because can it infer that? And I don't know. Like I think there was some discussion about it in the proposal whether it would be possible to just write ranges to vector instead of vector of int and infer that because in principle the information is there. I don't know the status of that. But we could also very easily write is an expect array that takes a container, right? And then takes the function and it will directly do that for us, right? So yes, we can do a bit, like we can make that more convenient. I think we also have like instead of explicit cast vector and the things in the library, we also have make vector, which just takes a bunch of ranges and creates a vector using the common type of all of those ranges and so on. So we can get rid of omitting the type. I just brought the simplest possible here.
Can I ask
Sure.
So if we had a std vector of, if we start with a std vector of int, could we create that expect array object?
So,
like if we had, say, reflection, for instance.
Yeah, so we have a std vector of ints, and we just want to. I'm sorry.
So if we started with a std vector of int, could we infer the expect array, like the ints?
Oh, so essentially, like we have a std vector of int variable, and we want to say assign that one using the JSON. We cannot like infer the middle, the expect number int. That one doesn't work because we might not want the ints directly, right? We might want to have the ints doubled, or we want to have an object in the array, and we only want to extract the int from there. But we can also do is in that case, examples will also have that we can have consign where you can assign a vector to range that way. Okay. Anything else about vector conversions? So objects. So here's again our JSON object, and we want to have something like expect key, right? So we've got an object, we expect the key, then ID, which we don't care about. Then we've got the name, so we consign the string to the name. We've got the speaker, so which can be optional, let's say. So we assign the boolean, and then we've got the talks key and so on. And while it would be possible to sort of implement an API like that, that is not a really good idea, because in JSON, the member order of an object is arbitrary. I can take a JSON string, change all the orders of the sub-objects in your thing, and I will still have the same JSON value, right? Conceptually, the order doesn't matter. So it's really bad to write code that sort of assumes a specific ordering of the keys. Because there's no guarantee to have them. So we don't provide an expect key to sort of not encourage this sort of behavior. So we want to sort of force you to write code like that, which does a loop and then does the comparison, handles the appropriate data, and skips everything it doesn't care about. But that's not that's verbose, right? Can we make that a bit nicer? And sure, we can write another algorithm for that. And the interface we decided to provide was expect object takes a bunch of, we call those groups. For example, we want the name. And so this is required. So we say CJSON required, name, and then we give a lambda. And this lambda will be invoked after we've seen the name key. And it will then get the string, or pull the string out of there, and assign that. We've got the speaker, which is optional. So if we have this key in there, then we invoke the lambda at that position. It will pull the appropriate value, assign it to the result. But if it's not there, it's not an error. The first one will invoke the error handler when the key wasn't found after we're done with the object. And finally, then we've also got the talks, which is also required. And here we want to countersign the talks. And again, we expect an array and compute the data. And so the idea is that we provide this function. And this function will be invoked after we've seen the particular key to pull the appropriate data out of the JSON. Required can take multiple of those things. So here we've got two different kinds of JSON that we want to pass. Either the value is a number, in which case we can expect a number, or it's a string. And so we can say, OK, so we've got the value object and then a sub-object. And we either got the number, and we do expect number, or the string, and then we do expect string. And required sort of means only one of those must match. Like if we've got both a number and a string, remember, that would be an error. And optional sort of means at most one, right? So it's fine if none of those matched. And again, the implementation is not that hard. So expect object just takes a bunch of groups. Then we expect an object which skips the curly brace. Then we do the loop over all the keys, pass the key to each group to check whether the group might be interested. And if none of the groups are interested, then we skip the value and continue on with whatever's the next one. And in the end, we call finalize to do error reporting. So this is sort of the group for required. So we store all the keys, which is sort of the pair between the name and the lambda. And then the parse function gets invoked with the key name we've just seen, checks whether we matched any of the key names provided. If so, we invoke the function to do the actual parsing. And if we matched multiple times, then that is an error. And in the end, in finalize, if we never matched, then that is also an error because one of those keys was required. And the optional group implementation is the same. We just do nothing in finalize. And for that, we sort of have this higher level API to parse objects out of the data. And this is in some situations it is still a bit of a both, like the countersign expect string, but we can write even more higher level algorithms to handle common cases like that. We provide a bit of convenience, so we often have JSON objects that only contain a single key, and then we don't want to use an output parameter to assign them. We want to directly return them. So we have this expect single member object, and the value it returns is then forwarded on to the caller. So this will give us the vector of ints directly from the JSON data. Questions about that one? Yes?
So I'm trying to make sure I understand.
Yeah.
So if you pass multiple arguments to required,
Mm-hmm.
it enforces exactly one?
Yes, exactly one. Required means exactly one of those. Yeah. Okay. And we can write many more algorithms when required. For example, they are not part of the libraries. They are just ideas that we can write when we need them. Like, for example, we've got a JSON, and the value can be null, or it can be something else. So we can write a function that pulls null and returns null opt, or invokes a function to return the actual thing. Or we say we have an array, and it always has 3 elements, so we can return a std array by invoking the function 3 times for each element, collecting the results in the array, and returning that to the caller. We can also support heterogeneous arrays, so we can have expect tuple that invokes the function with sort of the integral constant index, and then the function is an overload set that we can return different types. So for example, a function called with size t integral constant 0 can call expect number and return a number, but called with size t1, then it can call expect string and return a string, and then expect tuple will give us a tuple of int and string, right? And that way we can parse heterogeneous arrays of a given size when we have a particular order. And maybe in 30 years or so, when C++ has a reflection, right, we can write a function that just takes in a struct and will pull the appropriate values out of this struct to set the appropriate fields, right? The point is, because we are having all of those algorithms, right, it's possible to write algorithms, right? We've got the iterator level of abstraction. It's very easy to write algorithms. We can extend the library however we want, like once we've got this core facility on there. So with that, let's do a recap and look at parser design. So what do we have learned? We've learned that a range algorithm takes a sequence, takes an input range and produces a sequence of output values. And we can have an ego algorithms like the C++98 one that collect all output values in a container. We can use internal iteration where we invoke a callback for each value as it's computed. Or we can use an iterator range where the user actively has to request a new value. And a parser also takes an input range and produces a sequence of parse events, right? So we've got the exact same sort of models of parsing. So we can create a DOM on AST, which is a container. Like we eagerly create all the parse events and create a tree-like structure. Because usually with parsing, we've got this sort of bracketing syntax in there, which creates like a tree structure. We can invoke, in a push parser, we invoke a callback for each event as we handle them, which doesn't require allocation, but makes it a bit annoying to use. Or we can use a pull parser, where the user actively drives the parsing, which makes it very convenient. And with that, I'm done. So here again, the library is open source. It recently has a JSON pull parser. We also have an XML parser. So for parsing XML, I will get it. It also behaves the exact same way. So it might need a bit more polish. Having the guy in charge of the open source library is at the conference currently, so he hasn't looked at that. And we've got a couple more algorithms, like we've got beta ranges, we've got algorithms, string handling, and so on. We're also hiring. So if you're looking for a job, want to work on that, we're hiring. And thank you. Yes, so you can now also come to the microphone.
Thank you for the talk. The question is, do you have benchmarks for other JSON parsers versus yours? Which one is faster?
Yeah, so there was like one benchmark in the beginning of the talk with like the popular ones right here. So this is just a basic benchmark. So be on the very left, and then we've got Loma and rapidjson and boost.JSON, and then simdjson. But the caveat there, simdjson doesn't do validation, so it's just work. But like benchmarks can all be tailored. Like it's faster. Like from the libraries we've tried, it's the fastest one in our use cases where we want the full validation.
Thank you.
Hi. So really cool about the pull parsers. I like that. So like I was thinking, right? There's TypeScript, and with TypeScript you can do schemas for JSON. If you were to generate a JSON parser from a TypeScript, like when you know, like, okay, this is a string, this is a string, this is like an array of integers, how much faster do you think you can get it?
Yeah, so one advantage of the pull parser is that we don't have this big switch over all the possible values because we expect a particular type. So we expect a number, then we don't need to check whether it might be a string, right? Because we called expect number. Whereas a DOM parser, we want to parse a value, so it checks, is it a true, is it null, is it false, is it this number, and so on. So we get rid of the string. So it's absolutely possible to create a TypeScript schema and then generate C++ code that calls the pull parser and does the appropriate ways. Right, and then we've got the exact same thing as we, like, it wouldn't be any faster because we still call, we know we've got a number, so we just call expect number. And then we still need to check for like errors, but we can assume that it's not a string, right?
Well, parsing an array of strings would be faster than parsing strings one by one.
Parsing an array of strings would be faster, yes. Yeah, okay. So we can do like an optimization when we know we've got an array of strings, and then we do a special case for that, yes.
Dispatch by key, like you do string by string comparison each one.
Yes.
You can do that better.
Yeah, well, so the current one does like string or string comparison, but like we can, that can be optimized. Like we know at compile time what all the strings we expect, and then we can create like a try or whatever to very quickly dispatch the appropriate one. It's currently just that one because it's.
Okay. Yeah. Well, thank you very much.
Yeah. So like there are a bunch of other JSON libraries that all provide like higher level interfaces, like directly to JSON in a struct. But like all of that facilities can be implemented on top of a pull parser. Right? We haven't lost anything by writing a pull parser. We can implement this higher level interfaces on top. Yeah.
Thank you so much for your talk. I guess when you were talking about the skipping to avoid Stack Overflow, you said you guys do some techniques. I was pretty interested in what kind of technique you guys could use for recursive.
Essentially, recursion only happens with arrays or objects, and we sort of have like a bit set of whether we're currently in an array of object. And then when we add something, like when we encounter it, we increment the bit set and sort of have like the bit sort of serve as a call stack. But we just need to remember, are we in an array or are we in an object? And then the bit set has a fixed size, I believe 256. So we only allow nesting up to 256 elements. And then we can skip over that. The code is on GitHub if you're interested.
Oh, okay. So there is still recursion, but it just
no, there is no like it's a flat loop.
Oh, okay.
And it uses like a local array to simulate a call stack. But there's a fixed maximum nesting depth, and if that's exceeded, that's an error that's reported to the handler.
Okay. Yeah, and then I guess other thing is just following up the previous question about the schema. So like. The pull-based model seems to be really ideal for, like, if you know the schema ahead. So like as I guess that's the previous. I didn't catch the name, but like why not use the DSO or IDL based like I guess like schema that could I guess like similar to the TypeScript schema. Like you could look at all the I guess user can define it prehand. I mean, I guess pull-based model can be used to implement that.
Yeah, exactly.
But
so we don't currently have any automation to sort of create like the expect object with the required named and so on. We don't have any automation to create that because like it's used like in a bunch of places like ad hoc. Like it's less friction to just write a couple of lines of code. Like we don't do like we have stuff like that fetches a stock image from a database. So we've got like a JSON string with like the name and then the data. Right? We don't have big objects. We've got lots of small ones where it's just not worth that in most cases to pull out the big guns and do like automatic code generation from a schema or whatever.
Thank you.
This was a really great talk.
Thank you.
Do you have this working on iOS?
So the library is header only. The part is all header only. It should work on iOS. There are some SIMD optimizations. I don't know whether they will then trigger on iOS, but in principle, there is nothing stopping it from working on iOS. Yeah.
So I waited to last to hopefully be able to ask 3 questions.
Okay, sure.
First is what version of standard do we have to be able to compile this?
Yes. So we always use the latest one. We are currently limited by MSVC support. So like in principle, like we're using C++ 20 features in the implementation. And as soon as we can internally switch to a newer MSVC, we will start using C++ 23 features.
So we couldn't use it if we're stuck on 17?
No, you wouldn't be able to use it. And we don't want to. Like this is one-to-one the code that we use internally. And we don't want to have any compromises to support that sort of thing. But like while the library implementation is nice, especially compared with the convenience that the rest of the things the library brings, like it's not that hard to implement like a basic JSON pull parser. Like JSON is such a simple format. I really wanted to bring across the idea of having, because pull parsers in general, I believe are such a nice idea, and I wanted to share that.
So based on your experience with the implementation, if I pulled it down and moved it where I wouldn't have too much trouble moving it to 17?
No, you shouldn't be able. Yeah, you should be able to just copy the files, get rid of a bunch of the includes. So I've given a talk about the things the library before. We sort of patch around a lot of C++ defects using macros. So we sometimes write a bit of weird C++ code that you would have to manually then turn into.
Great, thanks. And the next is, I noticed at the beginning it was basically you have the JSON document that in your pull parsing. Mm-hmm. Can you present the document in pieces as if it were coming across through a stream?
So in principle, it doesn't work with our implementation. But like in principle, there's nothing to say, okay, you want to pull a number, and then it can return like false when it's at the end of the input. And then you can say the JSON parser, here I've got some more data, add that, and then I pull the number again, and then it will. Like there is some caveat if it's like in the middle of something, then there might be like, but like we don't need that use case, so we haven't implemented it, but like the model totally supports it.
Great. And the last question is basically just because you personally are giving this talk. Have you used this to parse the output of the Clang JSON AST?
I have not used it to pass the output of the Clang JSON AST. I know we're asking that. I don't know whether I want to do that again.
Okay.
Yeah, but like,
Thank you.
yeah.
Hi, thank you for your talk. I wanted to ask if the library had any utilities for handling duplicate keys and objects, like for validation purposes or...
Yeah. So if we have a duplicate key in an object, you will get an error with using required and optional, because it only expects one of those. And if the name matches again, then this will be an error.
Thank you.
But there's like no way to say, okay, it's fine, just give the latest one or whatever. Like that is hard-coded to be an error. But like you can write your own on top of the lower level while loop to do whatever behavior you want. Right?
Okay.
Okay. We have other questions? So again, thank you.